Hello friends, and welcome to Webronaq. Here is a question worth sitting with. When did a computer last rewrite a piece of code that millions of professional developers depend on every single day? The answer is more recent than you might think. In this video, we cover sorting and searching algorithms, the absolute backbone of computing, from first principles all the way to cutting-edge AI discovery. We will build real intuition, trace real examples, and by the end you will understand why choosing the right algorithm is an engineering decision with genuine cost and speed consequences out in the real world. Algorithms that seem like textbook exercises are very much alive and consequential right now. Let's get into it, starting with what sorting actually means and why it matters so much. Alright, let's start with the core idea. Sorting means rearranging a collection of data into a defined order, ascending, descending, alphabetical, whatever the task requires. Take the array 5, 2, 8, 1, 9, 4, 7, 3. After sorting it becomes 1, 2, 3, 4, 5, 7, 8, 9. Simple concept, enormous implications. Sorting algorithms fall into two broad families. Comparison-based algorithms, like merge sort and quicksort, work by comparing elements directly. Non-comparison algorithms, like radix sort, exploit the internal structure of the data itself to sort without direct comparisons, which can break through theoretical lower bounds in specific cases. Here is the key insight that runs through this entire video. Sorted data is the foundation for fast searching. You cannot run an efficient search on chaos. Next, let's look at the three specific sorting algorithms you will encounter most. Now look at this. 3 algorithms, 3 very different approaches. Bubble sort is the classic beginner algorithm. It repeatedly compares adjacent elements and swaps them if they are out of order. For our array 5, 2, 8, 1, it would compare 5 and 2, swap them, then compare 5 and 8, leave them, and so on. Dead simple to understand, but it runs in big O of n squared time, meaning performance collapses quickly on large inputs. Merge sort is the divide and conquer champion. Split the array in half, sort each half recursively, then merge. It guarantees big O of n log n time. Timsort is the practical hybrid Python and Java both use as their default. It scans the data for already ordered runs, sorts small runs with insertion sort, then merges them like merge sort. On real-world data that is often partially sorted, it can run in as little as linear time, beating naive n log n implementations in practice. Up next, searching. Here is the interesting part. Once your data is sorted, searching becomes dramatically cheaper. Searching means locating a specific target value inside a dataset. Linear search is the naive approach. Start at element 0 and check every element in sequence until you find the target or exhaust the list. For our sorted array 1, 2, 3, 4, 5, 7, 8, 9, finding the value 5 takes 5 comparisons. That is big O of n, fine for small data, brutal at scale. Binary search changes everything, but only on sorted data. Pick the middle element. If it equals the target, done. If the target is larger, discard the left half. If smaller, discard the right. Each step halves the search space. Finding 5 in our 8-element array takes just 3 comparisons. That is big O of log n. This is the direct payoff of sorting first, and it explains exactly why AlphaDev's work matters so much, which we will explore right now. Alright, let's bring this all together with a concrete example. In 2023, Google DeepMind published a paper in Nature introducing AlphaDev, a deep reinforcement learning agent that discovered new sorting routines and had them integrated into the LLVM-LIBC++ standard C++ library. That was the first time a reinforcement learning algorithm had ever been added to that library, and the first update to that part of the code in over a decade. AlphaDev's improvements focused on sort 3, sort 4, and sort 5, the routines that sort exactly 3, 4, or 5 elements. Those tiny routines are called inside every larger sort. The result was up to 70% faster performance for short sequences and about 1.7% faster for sequences exceeding 250,000 elements. Because sorting underlies searching, that speed gain cascades directly into faster search results, cheaper cloud bills, and quicker product rankings for billions of users worldwide. That is the real-world weight of an algorithm choice. So here is the big picture. Sort first, search fast. That is the through line of everything we covered. Bubble sort is your conceptual foundation, simple but slow at big O of n squared. Merge sort gives you reliable big O of n log n through divide and conquer. Timsort, the default in Python and Java, beats naive n log n on real-world partially sorted data by exploiting natural runs. Linear search works on anything but costs O of n. Binary search costs just O of log n, and it only works on sorted data, which is exactly why sorting matters so deeply. And as AlphaDev showed us, even a small efficiency gain in a foundational routine, up to 70% on short sequences, cascades into enormous real-world impact across cloud computing, e-commerce, and search. Algorithm choice is never just a textbook exercise. It is an engineering decision, with genuine cost and speed consequences. Thanks for watching Webronaq. See you in the next one.